Hi, everyone. My name's Jenny, and welcome to Measurement and Error Analysis for AP Physics. I am a science teacher from Massachusetts. I've taught a variety of different science subjects, including AP Physics 1 and AP Physics B. We've got a bunch of content to get through, so let's go ahead and just get started. So before we dive into the content, I want to remind you all to follow Think Fiveable on Twitter, on Instagram, on YouTube, to see when all the different streams are coming up and what different things you can take a look at and learn from. Some AP Physics streams that are coming up over the next week or so. Tomorrow night we have problem solving practice and Q&A with Casey Lee, and Casey is a student streamer, and she's planning on doing these problem solving practice Q&A combinations every Thursday night. So I'm hoping those get really popular because I think it'll be a good session with a lot of back and forth, and she'll be working on some practice problems from the regular content that we've covered over the course of the week. But then she'll also just have an open Q&A where you can ask all sorts of physics questions. And she's taken like 3 different AP Physics courses, so she'll be a really good resource. And then on the 8th at 7 p.m., we're going to look at the topic of acceleration. So hopefully that lines up pretty well with what you're doing in your classes with Christian Horner, another AP Physics teacher and AP reader. And then the following Thursday is another problem solving practice and Q&A with Casey again. So make sure to check those out and really, get into the AP Physics content. So in this stream, we're going to cover a couple of different topics. We're going to look at measurement in physics, and in that we'll look at the difference between dimensions and units of measurement. And we'll also look at the difference between scalar quantities and vector quantities. And then we're going to look at error analysis, which I think is super important. So we'll talk about why that's so important. We'll look at a couple different types of experimental error. We'll talk about how you define it. How do you calculate error, and then how do you report out that error in your experiments and data? So to jump right in, if we look at measurement and we think of dimensions versus units. So a dimension is a type of quantity. And so some examples of dimensions might be things like distance or time or mass. Those would all be dimensions that you can then measure using a bunch of different units. So the unit is how those different quantities are measured. So let's see if we can start to get some interaction in the chat. So if we look at the first one up there, the first dimension, distance, what are some units of measurement that you might use for distance? If you want to just type something into the chat. Okay, so we've got meters from Vanessa, kilometers from Charlie or Carly. Sorry if I'm pronouncing your name wrong. So yeah, and I love that you guys are defaulting to the metric system. That is perfect for physics, but it doesn't have to just be the metric system, right? So we could have meters, miles, centimeters, even light years if you're talking astronomical distances. What about time? Seconds. Yes, Vanessa is on it with like the base units. I love it. So we could have seconds. If we go bigger, we could have hours, days, centuries for huge lengths of time. And lastly, what about mass? See if we can get the base unit for that too. Kilograms, perfect. So kilograms, grams, milligrams. Notice there's not really quite as easy analog for the metric system when we're talking about mass. And in later lectures, we can talk about why that is and the difference between mass and weight and things like that. Okay, awesome. When you're converting, you wouldn't convert between dimensions. That's not really a thing, but you can convert between units of measurement. When you do, though, it has to be for the same dimension. So, for example, you can't convert years into miles, right? That doesn't make any sense. or grams into millimeters or something like that. And I put those two examples kind of deliberately because for a lot of people, the first one sounds really intuitive, like how many years are in a mile, right? That's a question that doesn't even make sense. But once you get into the units that we don't necessarily use every day, not everybody would say how many grams are in a millimeter. That wouldn't, jump out as quite as much of a cognitive dissonance type question. It might seem a little bit more reasonable, but if it's not the same dimension, you still can't actually convert it. But you can convert years into seconds or grams into kilograms or meters into miles or anything, as long as it's the same dimension, you can convert between them. And I didn't put it in here, but if anybody wants some practice going through unit conversions, whether it's metric to metric or metric to standard, let me know in the chat, or you can hit that ask a question button, and we can come back to that a little bit later, and we can kind of see if that's something that people want to talk about a little bit more. So if you don't see it, down at the bottom, there's a button there called ask a question, and I'll see a little notification when people ask questions, so I'll know that that's something that we want to come back to. And you can also go in there and upvote other people's questions, so I can see 10 people are interested in this, and so that's I'll make sure we really get back to that. So use that button. It's a good tool. Scalars versus vectors. Okay, so this might be something, if you've taken a physics class before, or if you might have already covered this if your class has been going for a little bit, depending on when you started school. The difference between a scalar and a vector. A scalar is a quantity that only has a magnitude or only has a size. Okay, so some examples of scalars would be mass, and time would also be a scalar. And so a vector, to contrast, would be a quantity that has both a magnitude and a direction. So if we go back to the examples of scalars, if you say something has a mass of 10 kilograms, it doesn't make any sense to say 10 kilograms to the right or 10 kilograms, downward or something like that. It doesn't make sense to have a direction to it. Same thing with time. You can maybe argue that time has a direction, but it's one direction, especially as far as AP Physics 1 is concerned. It's time goes one way. You wouldn't say, we had 5 years passed in the left direction or east or something like that. It doesn't work. But quantities like velocity or force or acceleration, these all have both magnitudes and direction. So you can say a velocity, you're going 20 meters per second upward, or 20 meters per second at 33 degrees. So you could express the direction in that way as an angle as well. Are there any questions so far? Okay, again, feel free to pop into the chat or to hit that ask a question button, and there'll be a couple of times where I'll pause and just sort of check in, because I don't want to just blast through and keep going if people want me to slow down a little bit. There are a number of quantities. Oh, I have a question for you, sorry. So what does a vector have that a scalar does not have? You can answer this one in the chat as well. Yeah, it has a direction. Okay, perfect, thank you. So there are a number of quantities that have sort of a scalar and a vector equivalent. And so sometimes we might use one as sort of shorthand for the other, but it's important that we know which one we're talking about. So for example, speed would be the scalar version. Okay, a speed is just the magnitude, 20 meters per second, 70 miles an hour, full stop, okay, with no direction attached. If we add a direction to it, then we would call it a velocity. Okay, so 70 miles an hour north or something like that. That would be a velocity as opposed to a speed. It's really common to just say speed when we mean velocity, but we should kind of try to be precise and know which one we're actually talking about. Similarly, distance is a scalar quantity. So we could say a distance of 30 meters or something like that. A displacement is the vector version, and a displacement is really best defined as the difference between a starting position and an ending position. So you started in one place and you ended 30 meters west of where you started, or something like that. So again, it's kind of easy to like get a little loose with those and to just use one when we mean the other. But if we want to be precise, the distance is the scalar quantity, the displacement is the vector quantity. And there's a later stream coming up, I believe next week, all about position and velocity and what those are and how they work and everything like that. So you can check that one out next week as well. Okay, so I want to make sure we have like a hard pause for any questions before we move on to talking about error. Okay, cool. I think you guys are pretty on it as far as the measurement stuff is concerned. Okay, so let's look at error. So if we're thinking about what is error, why do we care, why do we need to analyze it when we're thinking about experiments? An error is anything that could cause a measurement's value to be different from the true value of whatever it is you're trying to measure, whether it's a distance, whether it's a time, whether it's a mass, whatever. So these could be things like instrumental things, so something wrong with the piece of equipment or the instrument that you're using to measure. So it might be a really simple example would be a ruler where the markings are not quite right, or like they're kind of wide or blurry and are not really easy to read, or a scale that isn't zeroed properly or something like that. So errors with equipment. You could have some sort of physical reason why you can't quite get the right measurement. And then operator error is a real thing. So when you're reporting error in an experiment, or when you're talking about sources of error, you should never just say it was, user error or operator error or something like that. You should always try to be more specific and say things like, what did the user do, or what did the operator do that caused the error, and try to be as specific as possible. I don't know. I feel like that was always a pet peeve of mine in lab reports, where someone would be like, oh, our experiment was off because of, user error. And it was like, I need a little more information. But yes, an operator, the person using the equipment, could do something incorrectly, could do something wrong with the measurement, and you could get an error that way. And why it's important is why it's important to analyze error is it lets us see how reliable our data is. So if the data is the thing that you are using to draw a conclusion from in an experiment, right? And you'll see that on the AP exam. You'll have these experimental design questions where, you'll be given maybe the bare bones of a setup, or you'll be given a job. A group of students wants to determine X, and you have to come up with the experiment that will allow you to determine that. Well, if you're designing this whole experiment to determine it, during that experiment, you're going to be collecting data, and it's important that that data is reliable. Otherwise, you can't really draw good conclusions for it. And so that kind of negates the whole purpose of doing the experiment in the first place. So error analysis is very much a big deal. And I know the AP Physics course has, after it was redesigned and kind of split up from that big Physics B course and broken up into 1 and 2, that along with that came a really big emphasis on looking at data and designing experiments and doing inquiry type stuff. And so thinking about error and how reliable your data is became a really huge deal. So it's something that you should be thinking about all the time as you're doing experiments in your classes. So let's look at the concepts of precision versus accuracy. So one way to define precision is to say it is how repeatable a given measurement is. Okay, so you measure the same thing multiple times and you get the same result every time, which is not the same thing as accuracy. Accuracy is how correct that measurement is. It's possible to measure the same thing a bunch of times, get the same answer, get the same measurement every time, so your data is very precise, but you get the same wrong measurement every time. And so your data might be precise, but it is not accurate. And so if we look at the pictures that we have here, A, B, C, and D, we have these little targets and bullseyes. You may have seen something similar to this. This is kind of a pretty standard representation of looking at the difference between precision versus accuracy. If we look at A, we have all these little marks where I guess the arrow hit the target, and they're very close together, but they are not actually at the bullseye. So we would say that A is, it's precise, but it's not accurate. So let's go through the rest of them in the chat. So if we look at B, what do we think? Is that precise and is it accurate? Anybody have a guess? Well, we might ask if those marks, are they close together? Like, is the person hitting the same spot on the target every time? Or are they a bit more spread out? So, okay, to me, they look like they're pretty spread out, right? So I would say that this is not precise. And if we take that spread and we sort of like visually average them together, where would they all sort of average out to be? It's not really on the bullseye either. So not only is it not precise, but B is neither, right? B is not accurate and it's not precise. So that's kind of like the worst case scenario there, right? You're not hitting the same place every time and you're not really zeroing in on the target. Let's see if we can try again with C. Does C look like it is accurate or precise? Yeah, for C, it's oh wait, I'm sorry, I'm not sure if which one you're answering. Oh, it looks like there was a little bit of a delay because I'm seeing answers coming in for questions I might have asked a minute ago. So I apologize for that. So we said B is neither right, and I'm seeing the answer come in now for C. It is accurate, but it's not precise. So they're all kind of all over the place. But if you, again, sort of visually average those out, they would kind of end up near the bullseye. So C, if you did enough trials, if we want to kind of come back to the experiment idea, if you did enough trials and you averaged out all your results, you would probably get pretty close. So it would be accurate, but it's not precise. You're not getting the same answer every time. Okay, and then lastly, we can look at D. Both, yeah. So we can already see that D is like what you would want. If you were, doing archery, you would want your spread to look something like that. I don't do archery, so I guess I don't really know. But it's both. It's accurate, they're in the bullseye, and it's precise. They're nice and close together. So that's kind of what you're going for. Now, if you're doing an experiment and plotting your data, it's not really going to look like a target and a bullseye. So I kind of like this example even better. This looks a little bit more like something that you might actually see in a physics class during an experiment. So if we think of each of these as a line graph, so something, some quantity graphed over some other quantity. So maybe it's velocity over time or, something along those lines. And if we think of that horizontal line in the middle as what we're expecting as like the target data, we're expecting the quantity to stay constant over time at about that middle location. So let's see if we can kind of do the same exercise for each of these. So for A, does that look like it is precise and does it look like it is accurate? Now I'm seeing Vanessa say neither and question mark, but yeah, you're right. A is neither precise nor accurate. So not only is it, there's a lot of instability there, it's kind of all over the place, but it doesn't even, the instability doesn't even really center around that target line that we'd be looking for. So we would say that A is not accurate and it's not precise. So it's, in this case, maybe instead of the word precise, you might say stable, but it's not accurate. It's not where you expect it to be, and it's not a stable measurement. It's jumping around quite a bit. There's a lot of fluctuation there. Okay, so I think we've got the pattern. What about B? Yeah, B is precise, but it's not accurate. So the data is very stable. It's not fluctuating very much at all, but it's not what we expect it to be. It's a bit consistently higher than that line there in the middle. So precise, but not accurate. Okay, what about C? Okay, Vanessa is on it tonight. Yeah, C is both. It is precise or stable. It's not fluctuating very much. And it is right on that line. It's what we expect it to be. And then you can probably get D sort of by process of elimination, but hopefully you can also see what I'm talking about in the graph. What do we think about D? Oh, neither. I don't know how easy it is to type long answers in the chat there, but I'm curious as to why you would say neither for D. So there's kind of a little bit of interpretation here. I said it's accurate, but it's not precise. But you could kind of maybe make an argument either way. So why I said accurate and not precise is because roughly, hopefully, there's as many data points over the line as there are under the line. That was kind of the goal when I was drawing it anyway. So it is fluctuating around that center line. Again, if you averaged it out over time, you would get something that is pretty much on that target line. So it is hopefully accurate, but it's definitely not precise or not stable. There's a huge amount of fluctuation in this data. And maybe if you tried to draw a trend line through that, it wouldn't quite be at that middle line. You're kind of at the mercy of Google drawing tools, to be honest. But the intention was that it would be accurate and not precise. But that's how you want to sort of think about it. If you were to draw a trend line through that data, where would it be? That can give you a sense of whether or not it's accurate. And then sort of just visually, you can get a sense of whether it's not precise or not, or whether it's stable or not. Are there huge fluctuations or are there not? So if we want to, I'll take a minute for any questions on precision versus accuracy before we go on just a little bit. Okay, just wanted to make sure it's clear. Again, if you have any questions, pop them in the chat at any time. So the next two concepts we're going to talk about are kind of related, and we'll do a couple of questions later on to sort of see if we can see the links between them. But we can classify different errors as either indeterminate errors or systematic errors. So if we start with indeterminate errors, an indeterminate error is an error without a pattern. So you make the same measurements a bunch of times. Sometimes it's way higher than it should be. Sometimes it's way lower than it should be. Sometimes it's a little bit higher than it should be. Sometimes it's a little bit lower than it should be. There's no real pattern. It's not consistent. What I mean by that, though, just to clarify a little bit, I'm saying the size or the direction of the error. So is it high? Is it low? Is it way off? Or is it pretty close but not quite there? Those are the things that will tell you whether something's indeterminate. The cause, you could know exactly what's causing it. You could know that, my scale has a broken spring in it, and so it does weird things. You could know exactly what the cause is, but still say that it's an indeterminate error if it's not predictable what the error is going to be. If it's not like, oh, it's always a little bit high or it's always a little bit low or something like that. So some things that could cause an indeterminate error. Operator error is a big one, right? If you don't really know how to use the equipment that you're using, or I won't say you, because you guys, of course, know how to use everything that you're using. If the person doing the experiment doesn't really know how to use the equipment that they're using, and they just, they don't quite get it right, you could get indeterminate errors that way. As we'll see in a second, you can also get systematic errors that way if they're making the same mistake every time. But operator error could be a cause of an indeterminate error where you don't know, there's no real pattern to it. Fluctuating conditions. So I can give you a real example from my life of this particular type of error. When I was in college, I did an experiment as my senior research project where I was I was reflecting a light off of reflecting a laser rather, off of a little thin sheet of, I think it was sapphire, and like measuring what percentage of the beam got polarized and what percentage of the beam did not. And we'd kind of fire the laser in one end and then have a light sensor on the other end. And I was getting all sorts of weird numbers that didn't make any sense. It was kind of jumping all over the place. And it turned out there was a shade in the window that if it was a windy day, it would be all over the place. And it would just like trash my experiment because you would get sunlight kind of coming in different ways. And so we ended up having to like almost board up the window. But so fluctuating conditions in where you're doing the experiment can sort of mess up your data, and sometimes in an indeterminate way as well. And then if you have equipment that just has some inherent variability in it. So if it's maybe older equipment, or if it's just, the type of equipment you would typically have in a high school setting is not what you're going to have in like a research lab or a university or something like that. So variability of equipment might be something that you guys will be dealing with, in person. So that's something that you might see. So how do you think you could reduce indeterminate error? So if you have something where sometimes you get a result that's a little bit higher or a lot higher, sometimes you get a result that's a little bit lower or a lot lower, how do you think you could try to minimize that effect in your experiment? And I can give you a hint that the concept of averages and averaging things out is very helpful in reducing indeterminate error, getting it closer to that accurate place. So theoretically, if your error is really completely random, and usually it won't be literally random, but if it's pretty random, then the more measurements you make, the closer you will get to the highs canceling out the lows, and you will eventually get to that average. So it's like, if you flip a coin 10 times, are you going to get exactly 5 heads and 5 tails? Probably not. But if you flip a coin, 1,000 times, you're much more likely to get something very close to 500 heads and 500 tails. So really, multiple trials is like the key for reducing that indeterminate error, or anything that's kind of random. If you just keep doing multiple trials, they should kind of zero in on what the accurate result would be. The other type of error you might have is called a systematic error. And this one is something that has a similar size and or direction for every measurement, usually both. Systematic error is a lot harder to identify in an experiment because your data will still be precise. It'll still look good, right? You'll still look like you're getting the same thing because you'll get, or look like you're getting the correct thing because you'll get the same thing every time. But it is easier to correct for if you know what the error is, then you can correct for it. And the best example I have for systematic error is the car I used to have, where the speedometer consistently read 2 miles per hour slower than what I was actually going. I think that was actually a weird safety feature, I guess. But so if I was going 50 miles an hour, then my speedometer would say 48. If I was going 75 miles an hour, my speedometer would say 73, consistently every time. So it was wrong. There was an error, but it was wrong the same way every time. And so I could just look at it and mentally add 2, and I knew how fast I was really going. And so that's what I mean by it's harder to identify. So if I hadn't had some other way to know how fast I was going, I would never have known that my speedometer was off. But it's easier to correct for because I can just say, oh, add 2. So some causes of systematic error might be operator bias. So I kind of just to kind of hopefully make it clear, for indeterminate error, I put operator error, meaning, the person just doesn't quite know what they're doing and they're making a variety of different mistakes. Operator bias might be, consistently making the mistake the same way every time. Okay, so if you are, to give an example from maybe biology or chemistry class, if you're reading a liquid in a graduated cylinder and you don't know where to read the meniscus, you might get a consistent error every time because you're reading, a little bit higher or a little bit lower. Similarly, a consistent defect in the equipment. If your scale isn't zeroed properly, then you're going to get a little bit of extra weight every time because, maybe when there's no weight on there, it's reading 0.3 grams or something like that. So anytime you make a measurement on that scale, it's going to be 0.3 grams higher than what it really is. If you know that's the case, it's easy to correct for. But if you didn't realize that you forgot to zero your scale, then you're just going to keep going because you're not even going to know that there's something wrong. So that's kind of the good and the bad, I guess, for systematic error. To reduce systematic error, running multiple trials isn't going to work, right? Because if you're getting the same type of error every time, you can run as many trials as you want. They're never going to average out to the accurate value. So in some cases, unfortunately, you might need to redo or redesign the entire experiment. So maybe if you're making a consistent mistake in the procedure, but it's one that you can't really correct, or it's one that you can't not make just the way that it's working, or if you have that consistent defect in a certain piece of equipment, maybe you redesign your experiment so that it doesn't use that piece of equipment. Maybe you try to get at what you're trying to answer, trying to get at whatever the concept is, in a different way. That's kind of the worst case scenario. If you're lucky, you can just correct for the error, right? So I can look at my speedometer and I can say, oh, it says 64, that means I'm really going 66. And so I can just mentally correct or on paper correct for the error. So let's look at a couple of quick questions to see if we kind of have a sense of what this is all about. So if your data is precise but not accurate, what kind of error do you think you probably have? Okay, hopefully the chat is still working. I know it seemed like we had a little bit of a glitch earlier. Does anybody have a guess for this first one? So you're getting similar measurements every time, right? Your data is precise, it's repeatable, but it's off. It's not where it's supposed to be. So it's like wrong in the same way every single time. What type of error does that describe? Okay, I'm going to go ahead and bring up the answers. I'm sorry if you're typing in the chat and it's not showing up to me. Hopefully it'll kind of correct itself again like it did before. Or if you're confused and you're not typing in the chat, then we can kind of go through and explain this. So if your data is precise but not accurate, you probably have a systematic error. Okay, again, it's not accurate, right? It's wrong, it's incorrect, but it's repeatable. It's being incorrect in the same way every time. Okay, so you step on the scale at the doctor's office and say it's just maybe not zeroed properly. I don't know if you have to zero the scales at a doctor's office, but there's something wrong with it that it, adds 5 pounds every time. So it's not correct. It's not telling you the correct weight, but it's consistently wrong in the same way. So that would be a systematic error. And conversely, if your data is overall accurate, if you take a bunch of measurements and average them out, and you get something that is what you're expecting to get, but there's a big range there. You have some that are higher and some that are lower, then you probably have an indeterminate error. Okay, so there's no real pattern to it. It's not consistent. And like I said before, in that case, the solution is really just doing those bunch of trials and taking that average and hoping that you kind of zero in on the right answer. Okay, again, if I'm blasting through stuff and you have questions, please let me know, and hopefully the chat will be functioning. But we can move on a little bit and talk about how do you calculate error. If you've taken chemistry or even biology, you've probably seen this before, but basically there are 2 different ways that we might be calculating how much error that we have. One of those is percent error. So you've probably seen this before. And the difference between these 2, and I'll bring up the other one in a second, is not that one is better than the other, but it just depends on what type of data you have and what you're looking at. So if you have data where there is some sort of accepted value for comparison, like you're trying to do an experiment to determine the acceleration due to gravity. Like we know what the acceleration due to gravity is. We would use a percent error then with your results. And the formula for a percent error can be expressed in different ways, but kind of one nice succinct way to say it is the absolute value of the accepted value minus the experimental value, and then divide that by the accepted value. When you do that, you will, hopefully, unless you've got a lot of error going on, hopefully you will get a number that is less than 1. And you can think of that as a decimal version of your percent error, and then multiply it by 100 to convert it into a percent, or just move that decimal point 2 places. So if you have some sort of accepted value or some sort of target value that you're going for, then when you get your experimental value, you would use percent error to see how off you were. However, that's not always the case, right? Sometimes you are not comparing your data to some accepted value, some target that you were trying to get. Sometimes you're comparing your data to more data. So you measured the same thing a bunch of times and you got a kind of a range of values, and you want to see how close together were they? What's the percent difference between them? Okay, so this is kind of looking a little bit more at that precision value. How precise was it? How close were you to getting the same thing every time? And so there, a way to express that formula, and again, sometimes these are written in different ways, but the simplest way that I've seen is to think about the absolute value of the range, meaning the difference between the highest and the lowest values, divided by the average of all the values. And then again, that should give you a number that is less than 1, and then you can convert that decimal value into a percent. So let's look at a couple of examples. Okay, so our first one is the bounce height of the same ping pong ball is measured twice under the same conditions. So lab group drops the ping pong ball from the same height, measures how to the same surface, measures how high it bounces. And those 2 different measurements are 0.44 meters and 0.50 meters. So should you use percent error or percent difference when you're reporting these results? So hopefully, let's see if we can get, awesome. Chat looks like it's working. Okay, we can get an answer in the chat. You should use percent difference. So why should you use percent difference? I'm going to give you guys a little bit of time because it's longer to type it in. So I see, because it's measurements that you measured. That's true, but there might be a way to say that a little more clearly, or to, kind of add in a little bit more information. Like, what do you not have? What are you not comparing against in this case? Yeah, there's no theoretical value. There's no accepted value here. You don't know how high the ping pong ball was supposed to bounce. And so you're comparing data to more data. So you don't want to use percent error here, because neither of those values are more accepted or, correct than the other. And so you would want to use percent difference here. You'd want to see how close together were they. That's what you're really trying to find. Before we do the calculation, can you think of a case where you might use percent error for the same type of experiment? Like, what could have happened before you did the experiment to see where now you might want to use percent error? So let's say you knew something about this ping pong ball, right? You knew, how elastic it is, or something like that. You knew something about its properties. You knew enough to calculate how high it should bounce. So let's say you did the calculation first based on the properties of the ping pong ball. Then you did the experiment and did this bounce, measured the bounce height. Then you would actually have a theoretical value. You would have that calculated value that, okay, this is how high it should bounce when I do this experiment. And I figured this out based on, the properties of the ping pong ball, properties of the floor, that kind of stuff. In that case, you would actually want to do a percent error calculation. And that would be that accepted value, or that theoretical value. And you would average the 0.44 and the 0.5, and then compare your average to the thing you calculated using percent error. In this case, however, we just have those two data points, so we're just going to use percent difference. So if we look at the calculation, first we want to find the range. So absolute value of 0.44 minus 0.5, and then we divide that by the average. So 0.44 plus 0.5 divided by 2. And if we do those, we get 0.06 in the numerator and 0.47 in the denominator. And that comes out to 0.13. That's our decimal version of the percent error. And then we could convert that to a percent and just say 13%. Okay, so in that case, we'd say, the two values differ from each other by 13% or something along those lines. Okay, looking at another example. Okay, now let's say the Eiffel, let's say, this is actually true. The Eiffel Tower is, in fact, exactly 300 meters tall. I Googled it. So we have a group of students are using the shadow of the Eiffel Tower and some trigonometry to measure its height using, the length of the shadow, the angle to the sun, etc. So they do that, and they get a result of 287 meters. So in this case, should they use percent error or percent difference? Okay, this time they should use percent error. So why? Yeah, in this case, there is a theoretical value, or there is an accepted value, or whatever term you want to use to say it. We know how tall the Eiffel Tower actually is. So there is something that is objectively correct for us to compare our data to, or for those students to compare their measurement to. And so in this case, percent error is the right choice because you have an accepted value to compare it to. So again, if we go through this calculation, we would do the difference between those two values, the absolute value, rather, of the distance between them. So the theoretical or accepted value minus the experimental, or the one they measured. So 300 minus 287. And in this case, we're not dividing by the average. We are just dividing by the correct or theoretical or accepted value. So we want to know how far away from that number are we. So that's what we want to put in the denominator. It's not how far away from the average are we, it's how far away from this target value. And so then we get 13 divided by 300, and we get 0.043 or 4.3%, which is pretty impressive for measuring a shadow and trying to use the line of the sun. Yeah, not a real experiment, so we can make it as impressive as we want. Okay, the last thing we can look at with thinking about error is now we kind of see some different ways of how to calculate it, but how do you report that in your experiment? And most of the time you're going to use the percentage, and I'll show you what that looks like. But sometimes you might use what's called an absolute error, where in this case it gives the actual range of the data. So what that would look like is if you're measuring a time, for example, you might say 5.6 seconds plus or minus 0.5 seconds. So it tells you, it might be as high as 6.1, or it might be as low as 5.1, right? So it's telling you it's off by this amount. This is maybe less common in science, but it's certainly very common, in election data, for example. If you're looking at polling results, you could say this poll has a margin of error of, plus or minus 9 points or something like that. So you probably won't see it too much in physics, but it is a real thing. Think of expressing error in terms of absolute error. More often, you will see relative error where you're using the percentage. So there, for the same data, you would say 5.6 seconds plus or minus 8.9%. And these are actually expressing the exact same quantity. 0.5 seconds is 8.9% of 5.6. But this is probably how you'll see it expressed much more in a physics experiment, or really any science experiment. You'll see it as off by a percentage. Okay, I have one more kind of a little bit more detailed example that I'd like to look at with you. Before we do that, though, that's kind of the end of the actual content that I had. So now would be a good time if anybody in the chat has questions or comments or something that they would like to bring up before we kind of look at just one more slightly more detailed example. Okay, so if anything comes up, then feel free to type it up in the chat, and I'll kind of keep an eye on that. But I want to look at an example that can kind of put some of this in perspective and think about, okay, what does it actually look like in context, in an example? So I'm going to give you this example of a very, very simple experiment involving a pendulum. So let's say you had a pendulum and you had it attached to some sort of anchor point, and then I wish I had a physical thing here, but you would have a string hanging down and a weight at the bottom, and then you can lift that weight up to a certain height and drop it and let it swing back and forth. And the period of a pendulum is the time it takes to make one complete swing, all the way to one side and then all the way back to where it started. So let's say you want to do an experiment to see if I drop it from different heights, will it make it take longer to swing back and forth? And so you first lift the pendulum up to 0.10 or 0.10 meters or 10 centimeters. You let it go, time the period, do the same thing at 15 centimeters, 20, 25, and 30. And then you graph your data period over the drop height. So we got a nice little graph here. So what trend do we see there? If we did this experiment and we had no idea what the answer was, what kind of conclusion would we draw from the data that we have in front of us? So maybe another way to phrase it is, as you increase the drop height, what happens to the period according to this data and according to this graph? Okay, so we say increases. So yeah, based on this data that you have in front of you and knowing nothing else, it looks like the higher you drop it from, the longer it takes to make one complete swing back and forth. You can see sort of this upward curve in the graph. It looks like it's trending upward. But here's where analyzing error is kind of a big deal. So let's say that you had the same exact data, but now I told you that there is some inherent variability in the stopwatch that was used to time the swings. And in fact, that variability gives it a range of 0.3 seconds. So it's not particularly accurate, right? It could be 0.3 seconds or higher or 0.3 seconds lower, 0.3 seconds in either direction. So how might this affect the way you interpret this data? Or let me ask this. If we look at the numbers we have for the period, what's the difference between the highest amount of time and the lowest amount of time? It's 0.19, or actually, if you look below, I think you're looking at the 0.83. If you look below it at the 0.82, it's actually 0.2. That second one is a little bit even lower, but same basic idea. It's 0.19 or 0.2 seconds is the spread in the entire range of data that we got during the whole experiment. But we know that this stopwatch could be off by as much as 0.3 seconds. So what do you think that means about this nice trend that you're seeing on this graph, this like pretty upward slope that looks pretty convincing if you just kind of glance at it, or if you don't know anything about the error involved? So if the lowest number on this graph and the highest number on this graph are only about 0.2 seconds apart, and yet the stopwatch that was used to actually time these numbers could be off by as much as 0.3 seconds, you might have this nice shape on the graph, and it might look like you can draw a pretty solid conclusion from it, but it's really entirely meaningless. Like any of these points could actually be 0.3 seconds higher or 0.3 seconds lower, or even if we want to be generous and say that the 0.3 is like the total. So maybe it could be as much as 0.15 higher and 0.15 lower. If you play around within those margins with these data points here, you can make any shape really that you want, right? So you could make this graph look like it goes down. You could make this graph look like it's a horizontal line. You could make it look like a crazy zigzag. It looks like there's a nice trend here, but it doesn't really exist. And the only way you would know that is if you took into account the error. So certainly not when you get to the AP level, but I see this a lot, even like maybe in middle school science classes or freshman year science classes or something. You'll do this whole experiment and you will have just this tiny like little cursory discussion of error at the end. What are some of your sources of error? Oh, we could have had a user error or something, and then you just kind of leave it at that. But that's not enough, and that's certainly not enough when you get to the AP level. You really have to interrogate and say, what could have happened during my experiment that might make my measurement inaccurate or imprecise in some way? What might make the true value different from the value that I measured? You want to think about specifically what could have happened, maybe what you might have done, what could be weird with the experiment or the conditions in the room. And then think about how might that throw off my data? So maybe in this pendulum, maybe you could say, I was not super careful about dropping the pendulum carefully. Maybe I could have accidentally given it a push sometimes instead of just dropped it. Or maybe I could have accidentally like bumped it upwards sometimes instead of just dropped it. Or maybe there's something wrong with the stopwatch. Like we said in the very first slide, the point of analyzing error is to see how reliable your data is. And if you're going to draw conclusions from it, it really needs to be as reliable as possible. Because you might want to draw a conclusion from this graph that's completely wrong. Okay, if you just looked at this graph and you didn't think about error at all, you would say, if you increase the drop height, the period of the pendulum increases. And that's in fact not true at all. When you may have studied pendulums before. When you look at simple harmonic motion later on in physics, you will see that the drop height or the angle from which the pendulum is dropped actually has no effect on the period. If this was really accurate, you'd get a nice flat line where the period stays the same if all other conditions are the same as you alter the drop height. So you can really fall into a trap if you end up with something that looks like one thing, but you're seeing some sort of false conclusion there. So that's, kind of just a small example to kind of hopefully highlight the importance of thinking about error. So with that, our time is just about up. If anyone has any last minute questions or comments, then now's the time. Otherwise, I will remind you again to keep track of the different lectures that are going on, or the different interactive sessions that are going on, or the problem solving or Q&A. And you can find out about all of that by following Think Fiveable on Twitter, on Instagram, on YouTube, and by coming back here to Fiveable and checking out the different videos that are available. So thank you very much for your attention and your participation in the chat. It really is helpful when you're kind of getting that feedback. So thanks for that. And yeah, that's it. Thanks. No. Sorry about that.